Hi, I'm going to talk to you today about Bohr diagrams and how we model atoms and ions. So you learned a little bit about atoms in the last chapter. You learned that protons and neutrons are found in the nucleus of the atom and that the electrons are flying around the nucleus. A guy named Niels Bohr in 1913 said that the electrons move in definite orbits around the nucleus, sort of like the planets around the sun, and he put each electron in a specific energy level. Now we know today that the electrons don't hang out in these specified orbits like planets around the sun. They're more like bees buzzing around a hive. But his model, nevertheless, is extremely helpful for us as we try to understand something called ionic bonding. So on the left, you see a picture of the Bohr model of the atom, and you'll notice that he's got his nucleus in the middle, which has a positive charge, and there are also some neutrons in the middle, and those have no charge. So in the nucleus, you have your positively charged protons, and you also have your neutrons, which aren't shown in this diagram. Around the nucleus in specific energy levels are the electrons. And you'll notice that the electrons are just represented by dots here. They're negatively charged. There are 2 electrons in the first ring, which corresponds with the first energy level in Bohr's model. You can have 8 electrons maximum in the second ring. The third ring, you can have up to 18 electrons. Now, we'll never get that many in the third ring because once you start getting into more than 8 electrons in the third ring, things get more complicated, and I personally think that Bohr's model doesn't work quite so well. So for our purposes, we're going to have a maximum of 8 electrons in the third energy level. I'll explain a little bit more about that later. And as I said, electrons are found in these energy levels, but really they are not like planets around the sun. If you look at these 2 pictures, down here we have a picture of carbon, up here we have a picture of oxygen. The electrons are found in these things we call electron clouds. And in fact, if this was the size of your nucleus, about the size of, oh, I don't know, however big this is on a piece of paper, maybe it's about 1/4 inch across, the electrons would be in clouds that would be possibly a mile or so away. So the electrons really take up most of the space of the atom. Here are some examples of some Bohr models. The first example is hydrogen. Hydrogen has atomic number 1, and it has a mass of about 1.01 atomic mass units. Remember, when we round that to the nearest whole number, it becomes hydrogen's mass number. So hydrogen has a mass number of 1. I'll take that arrow out because this is the atomic mass. So the way you figure out how many particles are in the middle of the atom, how many protons and neutrons there are, we've already done this. You take the mass number, which in hydrogen is 1, subtract the atomic number, which, by the way, tells you the number of protons, and that tells you how many neutrons there are. So you see, the nucleus here is showing 1 proton, doesn't have any neutrons, and there's 1 electron here in the first ring. We always start our electrons from the middle and work out. Helium is element number 2 on the periodic table. Its mass is approximately 4, so its mass number is 4. Its atomic number is 2, so it has 2 protons, which leaves it 2 neutrons. So we've got 2 protons and 2 neutrons in the middle, and then these are neutral atoms, meaning that we have equal numbers of protons and electrons. So if we have 2 protons for helium, we also need to have 2 electrons. Protons are positive, electrons are negative. In a neutral atom, the numbers will add up to 0. Positive 2 and negative 2 adds up to 0. Here you see a model of nitrogen. Nitrogen is element number 7. It has a mass of 14. So it has 7 protons, 7 neutrons, and it's got 7 electrons. Now what I want you to pay attention to here is how the electrons go in. So the first 2 electrons go in the middle ring. The next 5 electrons go in the next ring, and they go in one at a time until you get 4 around the ring, and then the 5th one will double up. So we don't have any pairs of electrons in that second ring until we have 4 electrons, 1 on each compass point, basically. So a couple more examples. You see oxygen on the left. Oxygen has 8 protons, 8 neutrons, 8 electrons. See if you can check it out on the periodic table and figure out why there are 8 protons, 8 neutrons, and 8 electrons. You'll also know that the first 2 electrons go in the inside ring, and then electrons 3, 4, 5, 6, 7, and 8 go on the outside ring. You can have these pairs placed anywhere around this ring as long as you have 2 pairs and 2 single electrons. You're good. This element doesn't have a name on it. What element has 13 protons? You might remember that the number of protons is the identity of the element. It's the atomic number. So all you have to do is look on your periodic table, find element number 13. If you're looking, hopefully you found that it is aluminum. So this is a diagram of aluminum with 13 protons, 14 neutrons, because it has a mass of 27, which is equal to the total particles in the middle, and then 13 electrons. So you get 2 electrons on the first ring, you get 8 electrons on the second ring, and then your final 3 electrons go on that outside third ring. There's a really easy way to remember how many electrons you should put on each energy level. If you have a periodic table, which you will always have every time you take a test in my class, all you have to do is look at each row of the periodic table. So each row corresponds to an energy level. 1, oops, sorry, you can't see that. 1, 2, 3, 4, 5, 6, and 7. So the first energy level is the first row. There are 2 elements in the first row of the periodic table. The first energy level can have a maximum of 2 electrons. The second energy level, there's a total of 8 elements in the second row. So the second energy level can have a maximum of 8 electrons. Now the third energy level is where it gets tricky. The third row has 8 elements. So the third energy level for us is going to have 8 electrons on the third ring. If we were going to draw a diagram of potassium, we would put 2 electrons on the first ring, 8 on the second ring, 8 on the third ring, and then the final electron, electron number 19 for potassium, would go on the 4th ring. The reason on that other slide it shows that there are 18 electrons in the third energy level is because there are these elements here, which are really have their outer electrons as part of that third energy level. So you might notice that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements there. So those 10 plus this 8 makes a total of 18. But to me, that's where the Bohr model gets a little bit complicated. So we are not going to do any Bohr diagrams that go past element number 20 for calcium. So all of our diagrams will have 2 electrons on the first energy level, 8 on the second, a maximum of 8 on the third, and then possibly 2 on the fourth. So we'll just be diagramming up to calcium. The noble gases are a very special set of elements. You'll notice them here on the periodic table. The reason they're special is because all of the noble gases have their outer shell completely full. Helium, which is shown here, has 1 electron shell with 2 electrons, and if you remember, the first energy level could have a maximum of 2 electrons in it. Neon has 2 electrons in the first energy level and 8 in the second, so its outer shell is full. Argon has 2 electrons in the first energy level, 8 in the second, and 8 in the third. So again, because we're saying that that is full with 8 electrons, it's a very stable element. When elements are stable, they tend not to react with other elements. The noble gases used to be called inert gases because they didn't react with anything. Well, then chemists figured out how to get a couple of them to react, and now they're called the noble gases. Electrons are where chemistry happens. Electrons, it's because of electrons that chemicals react. And certain chemicals will react very violently because of the way their electrons are arranged. There's 2 ways that we'll look at that chemicals can react. One is an ionic reaction, and when you take 2 elements and they react together, they can form an ionic bond. Another way is for them to share electrons, and that would be considered to be a covalent bond. We'll be looking at both of those, but for today, we'll only talk a little bit about ionic bonding. In order to understand what ionic bonding is, we have to understand what an ion is. An ion is an atom that has either gained or lost an electron. Now remember, atoms are most stable when they have a full outer shell of electrons. So any atom will react with other elements in a way that makes it have a full outer shell of electrons. If you look at this picture, you see a Bohr diagram of sodium and a Bohr diagram of chlorine. You'll notice sodium's electron right here is in red. Sodium has 2 electrons in the first ring, 8 in the second, and then this one lonely electron on the third ring. Chlorine, in the meantime, has 2 in the first ring, 8 in the second ring, and 7 in the third ring. So it's got a space right here where if it only had an electron, it would have a full outer shell. If sodium could give away this electron, then that shell would go away, and the next shell is its full outer shell. That lends stability to both atoms. So what happens when you put sodium and chlorine together? There's quite a violent reaction, and one electron moves from the sodium atom to the chlorine atom. We get an ionic bond formed, and we get a compound called sodium chloride. Now this is so cool because sodium is a metal that you can cut with a table knife, and it's so reactive that if you put it on your hand, the moisture from your hand will make it start burning and you'll have an explosion. Chlorine is a poisonous green gas, but when that one little electron transfers, you get sodium chloride, which you can eat on your French fries. Here's another example of 2 elements that form an ionic bond. Magnesium has 2 electrons on its outside ring. Fluorine, just like chlorine, has space for an electron on its outside ring because it only has 7 electrons in the outer ring. So if we just had one magnesium atom and one fluorine atom, only one of the electrons would be able to transfer from the magnesium. So the way it works is one magnesium will react with 2 fluorine atoms, and each fluorine atom will take one of the magnesium electrons. Now when that happens, we get a magnesium ion and we get a fluoride ion. You might notice there's a difference in the name. Over here it was called fluorine, here it's called fluoride. Negative ions have names that end in IDE. So the name changes when the atom gains an electron. Positive ions keep their name. Now what do I mean by a positive ion or a negative ion? Well, if you count the protons and the electrons in each of these, you will see that they're no longer equal. Magnesium gave up 2 of its electrons. Magnesium originally had, let's see, 8, 9, 10, 11, 12 protons and 12 electrons. 12 plus negative 12 is 0. It's neutral. Over here, magnesium still has its 12 protons, but it only has 10 electrons. 12 plus negative 10 is positive 2. So that's a positive 2 ion. Fluorine has 9 protons and 9 electrons, a neutral atom. Over here, fluorine still has 9 protons, but now it has 10 electrons. So with positive 9 and negative 10, it adds up to -1. So fluoride ions have a -1 charge, and you'll notice that's written as a superscript. Magnesium ions have a +2 charge. I'm going to leave you today with this classic chemistry cartoon. I only have 17 electrons. I'd feel so much better if I had one more. I have an extra one. Here, you can take it. Wow, are you sure? Yes, I'm positive. Have a good day.